In this lesson, we will prove the fundamental theorem of arithmetic that says that any integer greater than 1 can be written uniquely as a product of prime numbers. But we will need to prove some theorems first. The first theorem we will prove is called Euclid's lemma. This theorem states that if a, b, and c are integers, and c divides the product a times b, and c is relatively prime to a, then c must divide b. So let's begin the proof. Since a and c are relatively prime, by definition, the greatest common divisor of a and c equals 1. But then there must exist integers x and y such that ax plus cy equals 1. So I can find a linear combination of a and c that equals 1. Then multiplying both sides of this equation by b, I see that a bx plus c by equals b. Since c divides ab, I can write ab as an integer times c. There exists an integer d such that AB equals D times C. So now replacing in the previous equation, we have B, which equals ABX plus CBY, can now be written as DCX plus CBY. So I replaced AB with DC here. But I can factor out a C from both terms. So this equals C times the quantity DX plus BY. So we see that B equals C times an integer. Therefore, C divides B. Now we will prove a corollary of Euclid's lemma. Let A, B, and P be integers. If P divides the product AB and P is prime, then P divides A, or P divides B. Let's see the proof. Well, if P divides AB and P is prime, and P doesn't divide A, then the greatest common divisor of P and A must equal 1. Why? Well, because the only positive divisors of P are 1 and P. So if P doesn't divide A, then P is not a divisor of A, and therefore the only other common divisor could be 1. So if the greatest common divisor of P and A are 1, then P and A are relatively prime. And therefore, by Euclid's lemma, P divides B. Therefore, P either divides A, or we've shown that P would have to divide B. The next corollary is an extension of the previous corollary. So if P divides a product A1 times A2 all the way up to AN, where the A's are integers and P is prime, then P must divide one of these A's. Then P divides AI for some I. We will prove this corollary by induction. So suppose there's only one factor that P divides. So the statement would be, if P divides just one number A1, then clearly P divides A1. So the statement is true. We've actually already proved the statement is true for n equals 2. This is the previous corollary. So we know that the statement is true if P divides a product of two integers. So now for the inductive step, we're going to suppose that the statement is true for integers n less than or equal to k. Then I'm going to show that the statement is true for n equals k plus 1. Then for n equals k plus 1, consider the relation P divides the product of k plus 1 integers. So I'm going to write it as a1 times a2 times all the way up to times ak times one more ak plus 1. Well, I want to think of this as the product of two integers, a1 through ak, times ak plus 1. Well, if I think of this as a product of two integers, and by the previous corollary, either P divides ak plus 1 or P divides the product a1, a2 up to ak. In this case, by our inductive hypothesis, P would have to divide ai for some I between 1 and k. So that demonstrates that P divides one of a1 through ak plus 1. Therefore, by the principle of mathematical induction, the statement is true for all n. Now we have all the information we need to prove the fundamental theorem of arithmetic. The fundamental theorem of arithmetic states that every integer greater than 1 can be written uniquely as a product of prime numbers. Every integer n greater than 1 is the unique product of primes. And when I say unique, that's up to the order of the factors. So every integer n can be written as a product of prime numbers p1, p2, up to pk. So for this proof, we're going to first prove the existence of a prime factorization for any integer n, and then for the second part, we will prove that this product must be unique. So first, let us establish the existence of a prime factorization. So suppose there are positive integers that are not the product of primes. Well, by the well-ordering principle, there must be a least integer that is not the product of primes. So by the well-ordering principle, let n be the smallest such integer. Then n must be composite, And then we can write n as a times b for some integers, a and b, with a and b between 1 and n. So 1 is less than a, which is less than or equal to b, which is less than n. Well, since a and b are less than n, then they must be the product of primes, because we assumed that n was the smallest number that was not a product of primes. So since a and b are less than n, a and b are the product of primes. But I can write n as a times b. If a is a product of primes and b is a product of primes, then I can write n as a product of primes. So n, which equals a times b, is also the product of primes. Which is a contradiction. So we've established that every integer greater than 1 can be written as a product of primes. Now we need to prove that this product is unique. So given an integer greater than 1, suppose I can write n as the product of primes in two different ways. So suppose n equals p1 times p2 up to pk. That also equals q1 times q2 up to ql for primes p and q. Then, without loss of generality, let's assume that these primes are written in increasing order. So, without loss of generality, assume that P1 is less than or equal to P2, which is less than or equal to so on up to Pk. And likewise, that the same thing for the Q's. So Q1 is less than or equal to Q2, which is less than or equal to QL. Well, by this factorization, we see that P1 divides this product of Q's. Then P1 divides Q1, Q2 up to QL. And this implies, by the previous corollary, that P1 must divide Qj for some j. Again, this is by the corollary we just proved. So P1 divides some Qj. But Qj is prime. So therefore, P1 must equal Qj. So P1 must equal Qj. Well, by a similar argument, we can show, if we start with Q1, we can show that Q1 must equal one of the P's. So similarly, we can show that Q1 equals Pi for some I. Then P1, which is less than or equal to this Pi, because they're written in increasing order, which equals Q1, which must be less than or equal to Qj, which equals P1. So by this chain of inequalities, we see that P1 must equal Q1. Thus, P1 equals Q1. And then in the first equation above, we can divide both sides by P1. So N divided by P1, or Q1, equals P2 times P3 up to Pk. And if I divide the Q's by P1 or Q1, I get Q2 times Q3 up to QL. But now, starting with this equation, I can show similarly that P2 must equal Q2. So starting over, we can show that P2 must equal Q2. And then we can cancel out P2 and Q2. Which equals Q2. Continuing this way, we can match up each prime P with a prime Q, and therefore they must have the same primes in their factorization, and each Pi should equal a Qi for all I. So continuing this way, we see that K must equal L. There must be the same amount of primes on each side. And Pi equals Qi for all I. And we can conclude that the factorization into primes must be unique. So the prime factorization of n is unique. And this finishes the fundamental theorem of arithmetic. So the fundamental theorem of arithmetic establishes the fact that we can write an integer as a unique product of primes. So n can be written as p1 times p2 times pk. But there are other ways to write this prime factorization. So suppose n equals p1 times p2 times all the way up to pk. And this is the unique factorization of n. Into primes. And we saw that it's okay to assume that P1 is less than or equal to P2, which is less than or equal to all the way up to Pk. Because if it's not, we can just rearrange the factors and we still have the same primes in this factorization. So we're going to assume in this unique factorization that P1 is less than or equal to P2, which is less than or equal to so on up to Pk. So these primes are not necessarily distinct. You could have a repeated prime in this factorization. But if we collect all the repeated prime factors using exponents, we can actually write this in a different way called the prime power decomposition. So by collecting all repetitions of each prime factor as that prime raised to a power we see that n can be written as its prime power decomposition which looks like n is q1, a prime q1 to the power a1 times q2 to the power a2 times up to qj to the power aj, where all the q's are distinct primes so where all the qi are distinct primes, such that q1 is less than q2 is less than so on up to qj, and all the a's are positive integers. So as a quick example, the number 36, which can be written in its unique factorization as 2 times 2 times 3 times 3, if I combine the repeated factors, we can write this as its prime power decomposition as 2 squared times 3 squared. So as a consequence of this, of writing integers in its prime power decomposition, we can have some alternate formulas for the greatest common divisor and the least common multiple of two integers. So suppose a equals prime p1 to the power a1 times p prime p2 to the power a2 times up to pn, prime pn to the power an, and some integer b equals p1 to the b1 times p2 to the b2 all the way up to pn to the bn. So where all the pi's are prime, and all the a's and b's are non-negative integers, then I can write the greatest common divisor of A and B as P1 to the power, which is, it's either going to be A1 or B1, whichever one is smaller. So P1 to the minimum of A1 comma B1 times P2 to the smaller of powers A2 or B2. So P2 raised to the minimum of A2 and B2 times each prime factor up to Pn raised to the minimum, the smaller of An and Bn. So for example, if A1 is smaller than B1, then we know that P1 to the power A1 will divide both A and B. Now we have a similar formula for the least common multiple. So the least common multiple of A and B, now instead of minimum of A1 and B1, this will actually equal the exponent on each prime will be the maximum or the bigger of each A and B. So the least common multiple of A and B will equal P1 to the biggest exponent that occurs, so the maximum of A1 and B1, times P2 to the maximum of A2 or B2, all the way up to the factor Pn to the maximum of An, Bn. So for example, if I have a prime power decomposition for A and B already, so for example, say A was 2 cubed times 3 to the 5th power times 5 to the 1st power times 7 squared, and I know that B can be written as 2 to the power 0 times 3 cubed times 5 squared times 7 to the 1st power, And notice if a prime doesn't occur in the factorization, then you can still include it in the prime power decomposition as 2 to the power 0, for example, or that prime to the power 0. Then quickly I can see that the greatest common divisor of these two integers a and b will be, again, we'll have the same primes, but I'll use the smaller of the two exponents. So 2 to the 0, 3 cubed, 5 to the power 1, and 7 to the power 1. The least common multiple of a and b will be, now this, I'll use the bigger of the two exponents, so this will equal 2 cubed times 3 to the 5th times 5 squared times 7 squared.